Hello and welcome to my YouTube channel. Today we are going to see how to program the ADC modules in the Tiva C board. Let us briefly talk about the ADC modules and its features which are available in the Tiva C board. Tiva C board supports 12 input ADC modules and each module features 12-bit conversion resolution. So that means it can go up to 2 to the power 12, that is 4096 steps or different levels. Each ADC module contains 4 programmable sequencers. We generally call them sample sequencers. And with these sample sequencers, we can sample multiple analog input sources without the microcontroller's intervention. So that means they can independently work without the intervention of the microcontroller. Secondly, each sample sequencer provides flexible programming and we can generate the events of ADC modules using different triggers, interrupts, sequence priority and all. These ADC modules support single ADNET as well as differential input configuration, and it can go up to 1 million samples per second. So that means the sample rate can go up to 1 million samples per second. It is a very high sampling rate. For the triggering purpose, we can use either software-based triggering, timer-based triggering, analog comparators-based triggering, PWM or GPIO-based triggering. Here the triggering means to start the ADC conversion. So that means to start the ADC conversion, we can use triggers from these 5 different sources. Now coming to the structure of the ADCs available. So there are 2 ADC modules, ADC 0 and ADC 1. Each supports all these features which are listed above. So we can provide the trigger to start the ADC 0 or ADC 1. And once the trigger is received by these modules, they read the analog voltage at the input channels. And then after conversion, they can generate interrupts to the microcontroller to inform that the ADC conversion has been completed. For more details, please refer to the data sheet. Now coming to the sample sequencers and ADC pins. Like I said before, there are 4 sample sequencers, sample sequencer 0 to sample sequencer 3. Sample sequencer 0 supports 8 number of samples and sample sequencer 1 and 2 supports 4 number of samples and sample sequencer 3 supports 1 sample. And the depth of first in first out registers, or we can say buffers, available in these sample sequencers are as follows. Sample sequencer 0 supports 8 buffer or 8 FIFO registers. Sample sequencer 1 and 2 supports 4 FIFO registers or buffers, and sample sequencer 3 supports 1 first in first out buffer. Now coming to the pins, which are most important while we make the connections in the Tiva C board. So A in 0 to A in 11, there are 12 ADC channels. Physically, these pins are the pin number 6, 7, 8, 9, 64, 63, so on up to 57. So these are the physical pins of the microcontroller, and these pins are connected to port E, port D and port B's input terminals. So remember, port E, port D and port B's two pins support the ADC conversions, also known by the name ADC 0 to ADC 11. Please make note of these pin numbers and the port numbers, because these will be very useful when you will be writing your program. So make note of the port number and corresponding pin numbers, and similarly the ADC channels which are available in the Tiva C module. Now coming to our case, in our case we are going to program PE0, that is port is 0th pin for this programming. Now coming to the steps used to program the ADC module. First we have to provide the system clock gating signals to the ADC module. In our case we will be using ADC 0, that is the ADC 0th module. Secondly, we will have to provide the system clock to the port E, because like I showed before, PE0 is the pin which we are going to program. Then we will have to configure the PE0th pin as the analog input, which is basically ADC channel number 3. Then we have to configure and enable the sample sequencer with a processor triggering to start the conversion. We have to clear the ADC interrupts once it is enabled. So after enabling the interrupts, we have to clear the status so that the next interrupt from the ADC can be generated. Then we have to trigger the ADC conversion, which means to start the ADC conversion, wait for the conversion to finish, and then read the value of ADC. So let us start the coding and see how to code the program to use the ADC module present in the Tiva C board. Like in the previous examples, we are going to use Code Composer Studio to write our code. So let me open the Code Composer Studio. It will take again maybe 1 or 2 seconds to upload the IDE. So I can start a new project by clicking this button, New Project, or File, New, CCS Project. Okay, so let me start a new project. I hope you know how to select the target and the connection in the Tiva C board. If not, please visit the previous videos of this playlist. Let me give a name to the project. So I am going to give the name ADC read PE0 and click finish to start the project. So here we have the project with us, and this is the main.c program which is generated by the Code Composer Studio. So let me just populate this main window with the comments that to be followed to complete the ADC reading. I am going to fill these comment sections one by one. Before that, let me add the library files for the programming. So go to the project, right click on the project, go to properties, then click on the include options, and here click add, go to browse, go to the folder where you have the TivaWare with you. In my case, I am going to use TivaWare C series 2.2.0.295. Click select and OK. Apply and close. So this will add the TivaWare in my project. Secondly, I will have to add the library file. For that, I can open the local C folder. Inside that, I have the TI folder where I have installed the TivaWare. Open the TivaWare folder, go to driver lib and open the CCS folder because we are using Code Composer Studio. Open the debug and click on driverlib.lib. This will allow us to add the library files required for this project. So here the option says either copy the files or link to the files. I generally prefer copying the files. So click OK. You may link the file. There is no such compulsion. Now, let us start writing the code. And first of all, like in the comment section, we have to include the important header files. So let me include the header files. So hash include std. So for auto completion, I will be using control space. So I press control space. It gives me all the options available in the Code Composer Studio. So first of all, I will add the standard int. Similarly, include std io.h, and then I will include std bull.h. So first these three header files will be included, and then we will include inc folder. Inside that we will have to include hardware memory map.h, then include inc folder and sw hardware types.h. Then we have to include driver lib folder. Inside that we have to include the sysctl because this will be used to enable the GPIO module and the ADC module. Then we include driver lib folder GPIO.h because we are going to use GPIO, and then include, wait a second, then include driver lib ADC module. For that we use adc.h, and at the end we use driver lib pinmap.h. So these are the header files which are included to meet the requirements of the program. Now let us create few macros so that we can use these macros instead of writing long parameters. So hash define ADC underscore reference underscore voltage. So remember, the reference voltage available in our ADC is 3.3 volt. Therefore, I am using ADC voltage reference as 3.3. Then hash define ADC maximum value, and we know maximum value can go up to 4095, which is 4096 minus 1. Basically this is 2 to the power 12 because 12-bit ADCs are available. Since 12-bit ADC is available in Tiva C board. Okay, then we define ADC sequencer sequence underscore num. So in this case I am going to use ADC sample sequencer 0. You may choose 0, 1, 2 or 3 depending on your requirements. Now let me populate the main folder. So first main function. So first of all, I will be populating the system clocks related functionalities. So first let me configure the clock settings of the microcontroller. For that, I'll be using some system control related files, and later we will be using ADC related files and GPIO related files. So let me add those important files. So right click on the project, add files, go to the driver lib folder inside the TivaWare because we are going to use ADC, then GPIO.c, and then sysctl.c, and that's all for time being. So I will open all these files. So ADC, GPIO, and sysctl. Let me start with the sysctl programming. So remember to open the outline window. So go to view, click on the outline window. Here on the right side, you can see the outline window. This window is very helpful to obtain all the functions available inside these C files. For example, if I open the sysctl.c in the outline window, I can see all the list of functions available with the sysctl. And with this, we can easily program our code, or we can easily program the ADC modules. So let me first go to the sysctl, and for setting the clock, I can go to sysctl clock set function. So sysctl clock set function. This function allows us to set the clock of our microcontroller, sets the clock of the device. So let me copy this function and populate this function. So copy this function, paste, semicolon. So in the config variable, we will have to use the parameters which are available in this function. Please go through this function if you have any doubt, and with this you can know which parameters I am using and why I am using these parameters. So let's start filling the sysctl function. So sysctl underscore sysdiv. So I am going to divide it by 2. So sysdiv 2, then or sysctl underscore use PLL. I am not going to use the oscillator this time. I am going to use the PLL. Then sysctl underscore oscillator main. Sysctl OSC oscillator underscore main. Okay, and then the last argument is sysctl underscore crystal 16 megahertz. So this will configure my clock of the microcontroller to work at 16 megahertz. Okay, now let us go to the next part, which is to enable the ADC module. To enable the ADC module, again we will have to use the sysctl's function to enable a peripheral. So to enable the peripheral, we will have to use sysctl peripheral enable function. If you want to go through the definition, it enables the peripheral, and here are the list of peripherals available. So let me just copy this function and paste it here, semicolon. In the argument, we can use the available list of peripherals. So because we are interested in ADC 0, we are going to use sysctl peripheral ADC 0. Copy this argument and paste it here. So this will enable the ADC module. Now let us enable the GPIO. For that again we will have to use the same function, but this time the argument will be GPIO E, because GPIO E will provide the pins for ADC 0. So let me copy this function again, Control C, paste it here and replace the argument with GPIO E. So now we have enabled both the clocks for both ADC and GPIO E. Next we will have to configure the PE0 to work as an analog input channel. For that I will have to open the GPIO.c file, and in the outline we can check GPIO pin type input, and rather than input we are going to use ADC. For that we have to select GPIO pin type ADC. So GPIO pin type LCD I2C, here GPIO pin type ADC. I will copy this function. This configures the pins for use as analog to digital converter inputs. So I will copy this function and paste it here, and we can see it requires two arguments. First is the port and second is the pin which we are interested in. So for the port, we know the port is port E, and then pin is pin number 0. So I can use GPIO underscore port E base. This is the port, and then for the pin I can use GPIO underscore pin 0. That means PE0. So we have configured PE0 to work as analog input using this function. Now for the configuration of sample sequencer in the third sample sequencer. So rather than I'm going for sample sequencer 0, because I have used sample sequencer 0. If you want to change, you can change this number and automatically all the configuration will be changed here in this function. So to work with the ADC, we will have to open the adc.c file, and to configure the sample sequencer, let us first open the ADC sample sequence configure. This function requires 4 arguments, and if you want to read the functionality, configures the trigger source and priority of the sample sequencer. So first of all, let me just copy this function ADC sample ADC sequence configure, copy this and paste it in the project. Now let us populate the arguments. First argument required is the base of the ADC. So ADC underscore ADC 0 underscore control space, you can see ADC base 0. Now coming to the sample sequencer number. So we have defined the sample sequencer number, ADC sample sequence number, which is 0. We have defined in the macro. Now the trigger source, for the trigger source we can use ADC underscore TRI trigger processor ADC, wait a second, ADC underscore trigger processor. Okay, and then last we have to select the priority, and let me keep the priority as 0 because here we are not using any other interrupt source. So I am giving the highest priority to the ADC for this program. If you have multiple interrupts, then you can change this number according to your choice. Remember, highest priority is 0. Now after configuring the sequence, we have to configure the step of the sequence. So click, and now we will use this function ADC sequence step configure. This configures the step of sample sequencer and it requires 4 argument. Okay, so let me just copy this function, copy and paste it here, semicolon. Now let us again populate the argument. So ADC 0 underscore base. So this is our first argument. Sample sequencer number, we know that is ADC underscore sequence number. Trigger source, we know the step number. For the step, we will use 0th step. Okay, step 0. And then for this last argument, we will have to use 4 different parameters to meet the requirements of UI32 config. If you read here, UI32 config comprises of 4 arguments. So UI32 config is the configuration of this step, and it is logical OR of this argument. So let me just fill this argument. So ADC underscore CTL channel IE CTL underscore IE, then or ADC underscore CTL underscore CH3 wait a second, CTL underscore control space CH3, that is the channel number 3, and then or CTL IE, then ADC underscore CTL underscore end. So this will configure the steps of the ADC sequencing. Now let us use the third function, which is to enable the sample sequencer. So open the ADC.C. Here we can see ADC sequence enable function. This enables the sample sequencer. So just copy this function. This is the last function to configure the ADC module, and put a semicolon at the end. Now, so here again we need 2 arguments. First is ADC 0 base, and then the sequence number. So sequence number, we know it is defined in the macro ADC sequence num. Okay, so this configures our sample sequencer 0 with a processor triggering, or we can say software triggering. Now let us clear the interrupt. So ADC, open the ADC.C, and we can check ADC int clear. So this will clear the interrupt of the sample source. Okay, so let us copy this function, Control C, and paste it here, semicolon. Again the interrupt base is our ADC 0. Wait a second, I have made something wrong here. Wait a second. By mistake, I just divided the window in 2 halves. Okay, so I just made the corrections. The editor was actually toggled split in horizontal, so I have fixed it anyway. Now we were working on this part, ADC int clear. For that we need the first argument to be the ADC 0, control space ADC 0 base, and the sample sequence, we know we are using ADC underscore sequence num. So this will clear the interrupt of the ADC. Now let us trigger or start the ADC conversion. For that, we have to use the ADC.C again, and in this we have to check where is the function for starting the ADC conversion, or we can say ADC triggering. So for that we use ADC processor trigger function. It causes the processor to trigger the sample sequencing, or in short, the ADC conversion will start with this function. Put a semicolon at the end, and let's populate. The triggering should be generated from the ADC 0th base, and sequence number we have defined ADC underscore sequence num. So this will trigger or start the ADC conversion. Now we will have to wait for the conversion to complete, because ADC or analog to digital conversion is not a simple operation. It requires multiple steps to be followed to convert an analog signal to digital. So we will have to give some time to the ADC to complete the process of conversion. So for that, I can use while function, and I will remain here until unless I meet the requirements or the ADC conversion is not over. So for that we can use again ADC, and we can check the status of the interrupt. For that, ADC int status, we will use this function, and we can see here gets interrupt status for specified ADC module. After the ADC completes the conversion, it will generate an interrupt. For that, we will use this function. Until unless the interrupt is generated, we will wait here in this loop. So again, we require two arguments. First is the ADC base. We know ADC base is ADC 0 base, and we can say, wait a second, not this function. So ADC interrupt status, so not EX, okay. So ADC int status, this one, my mistake. Okay, so copy this function, and this will get current interrupt status. So we'll paste it here. First argument is the base, so ADC 0th base. Sequence number, we know we have been using ADC underscore sequence number, and bool masked, that means whether it is true or false. So we will remain here till it is not true. So this function will remain in the while loop until unless the ADC has generated an interrupt. That means the ADC conversion has been complete. So after completion, we will have to clear the status of the interrupt. So we'll be using the function to clear ADC int clear. Okay, so copy this function, paste it here. So once the interrupt has been generated, that shows the conversion is over, and then we will have to clear the interrupt status. Otherwise, next time the ADC will not be able to generate the interrupt. So to clear the interrupt, again we need two arguments, ADC 0 base, and the sequence number we know again ADC underscore sequence. Okay, now this will clear the interrupt. Now let us read the status of the ADC or the value of the ADC. For that, first of all, let me just use uint32, a 32-bit variable which is integer, and I will give the name ADC value, and I will store the value of the ADC in this variable. So to read the value of the ADC, we'll use ADC sequence get data. Again, you can open the ADC.c, ADC sequence data get. This function will be using, and here it gets the captured data of sample sequencer. So we will use this function to get the value of the ADC. Now again, it requires 4 arguments. So ADC 0 base sequence number, we know ADC underscore sequence num, and the buffer where, or the pointer to the buffer where the value has to be stored. And we know we have declared a variable which is 32-bit. So we will use this variable or the pointer to that variable to store the value. So ADC value. So I can delete this part, ADC uint 32. Okay. So we have populated the function, and this will read the value of the ADC. Now we have read the value, and generally this value will be, or the value of ADC will lie between 0 to 4096. Because I am using a potentiometer, I would like to convert this number, which will lie between 0 to 4095, to its equivalent voltage. So ADC value will be between 0 to 4095. But this number does not make any sense if we are interested to know the voltage. So for that, we will have to convert this number to its equivalent voltage. To convert the ADC value to voltage, we will further use another variable, and I can call it voltage. Okay, and I will store this voltage value in the, not rather than integer, I can use float. It will make more sense. So I will use a float because this will provide me the values in decimal value also. So I will use this value to be stored in the voltage variable. So ADC value multiplied by ADC reference voltage, okay, divided by ADC max value. This will give me the value of the voltage in the PE 0th pin. Now after getting this value, we can wait for some time, or we can generate a delay for the next reading. So for that, I can use delay function, and we have to define this delay function on top. And for that, we will use sysctl's one function to get the clock speed of the microcontroller. For that, we can use sysctl clock get. We have been using it in the previous programs. So this function will provide me the clock rate or the speed of the clock of the processor. I will put it here, and because we have configured it into 16 megahertz divided by 10, so it will wait for this much time before the next value of the float will be, next value of the voltage will be read from the ADC. Now we have to define this delay function. For that, what I can do, I can go up, and here in the delay function I can start writing the delay function. It is not that difficult. We will just make a void delay function, and this function will take uint32 type variable as an argument. We call it iterations, and that means this loop or this delay will remain in this loop for the iterations, and here iterations will be obtained from the sysctl clock get value divided by 10. Okay, if you want to shorten the iteration or the value of iteration, you can go for divided by 20, 30, or according to your choice. Or if you want to make a longer delay, you can delete this divided by 10. Okay, now let us make the function. So I introduce volatile uint 32 underscore t I. This is my variable which I will be incrementing till the times for the I equal to 0 to I less than iterations I plus plus. So this program or the loop will remain in the delay loop for this iterations, and the iteration value will be obtained from this function. Okay, so this completes our coding part. Let me just compile it and check if there is any error. And we can see there are few errors. Expected a semicolon here. Yeah, so there is a semicolon missing here. Let me compile again. Must be a pointer. Here it says it must be a pointer. So ADC value, okay, so wrong, very sorry. Here I have to use the ampersand sign, because ampersand sign means to the address of ADC value. Let me recompile it. And okay, this is not a big issue. It is just a warning. Variable voltage was declared but never referenced. That's not a big deal. So we have created a program without any error. Let me use the debug mode to upload the program, and then we can see the value of variable in the expression window. I will show you how to get this expression window. For that, for example, if this window is not available, then in that case you can go to view, go to expressions. Let me just clear all the variables. So remove all. So with expression window, you can keep an eye on the values of variables. For example, if I want to know the value of variable voltage, I can select that variable and right click, go to add watch expression, click OK, and you can see voltage has been added here. Similarly, I can add the ADC value, right click, add watch expression ADC value. So now we have two variables which have been added in the project. I can keep a breakpoint. For that, come to the left side, double click on the line. Similarly, you can come here in the 72nd line, double click, and you can add a breakpoint. So the program will stop here. So before running this program, let me open my camera. I hope you can see the camera on the bottom right. I have connected the red wire to VCC and black wire to the ground, and yellow line is connected to port E0. And here I have the potentiometer. The value of the voltage from the potentiometer will reach to the PE0, and the value will lie between 3.3 to 0 volt. So let me just run the program. For that, I can click resume. Okay, so we have reached to this breakpoint. Resume. So float value 0, resume. Now we can see the voltage value is 2.02 volt and equivalent value for, or the count value is 2511. So click again. So you will get the value of voltage. Let me just change the potentiometer a bit and resume, and you can see the value of voltage will get changed. So before it was 2 volt, now it is 1012, the value of ADC, and voltage is 0.815 volts. Again, let me change the potentiometer and let us read the value of the voltage. So you can see the value is 0.8 volt and the count of ADC is 1024. In the next video, I will show you how to print these values in the UART. So we'll be using 3 peripherals. One is the GPIO, which will be controlling the UART, and the ADC. So ADC value will be read from the potentiometer and the value will be printed in the UART. I hope you have now understood how to program the analog to digital converter in Tiva C board. If you have any doubts or suggestions, please put your doubts and suggestions in the comment section. If you have not subscribed the channel, then I would request you to subscribe the channel and click the bell icon so that you can be notified whenever I upload a new video. With this, I would like to thank you and have a nice day.